So what we are going to do today is just kind of like an application of what we have learned so far. So I'm going to hack a program. And I will point out a few things that are kind of important before you start hacking anything. You might need to know about these things. Okay, so the first one is the DMCA. Okay, the DMCA, you can just look it up. DMCA, which stands for Digital Millennium Copyright Act, has been established a long time ago, since 1996, which is probably before a few of you were born, because I think we're starting to get to the generation where you guys were born around that time, if not later. So when you click on this link, which is Wikipedia, you will see what it is, what it talks about. Okay, the Copyright Act criminalizes production and dissemination of technology, devices, or services intended to circumvent measures that control access to copyrighted work. So this is basically, one of the main purposes of the DMCA is to curb people from researching, finding out, and then telling other people how to circumvent control access. So that would include decrypting your DVD, okay? And it is not the act of you decrypting your DVD, and pirating something that is illegal. If you find out how to do it and you just tell the whole world, it's like, oh, I found out how to decrypt DVD, that is criminal. Okay, even if you don't do it, okay, you say, okay, but I own these DVDs. I bought these DVDs. I have the receipt to show for the fact that I own these DVDs, and I'm just curious, doing some research, finding out how to do it. Nope, cannot do that either. Okay, the DMCA is, I think, unique to the United States. In other words, in most other countries, they do not have something like that. In most other countries, the act of pirating is illegal, but learning how to decrypt a DVD itself is not criminal. Okay, so there's a difference. All right, so that means if you're trying to apply what we learned in today's lecture to a program that is copyrighted, you probably will be in violation of the DMCA. Is that okay? Okay, so keep an eye on the DMCA before you do anything, especially if you want to publish your results and go like, see, this is how you circumvent the copy protection of something, or this is how you can use this particular program. It can be web-based, it doesn't really matter, without paying for it, okay, without actually having the authorization to do it. So keep this in mind, and with that, we are going to start hacking. Okay, so today we're going to hack a program that has a particular protection feature where you have to enter the password correctly before it can let you access the rest of the program. Now, this is just a toy program that I wrote, and hereby I grant myself the permission to hack my own program, so I'm not in violation of the DMCA anymore.
You might want to have a written copy just in case.
All right. So the program that I have is already uploaded to the Power server because of yesterday's class, so we'll just go ahead and use it on the Power server. This is the 32-bit version of this program. I have a 64-bit too, which is basically using the same technique to hack it. Okay. So the program is called hack132.stripped. Okay. The extension stripped is not really meaningful other than telling me that the symbol table is no longer here, which means I cannot cheat and go like, okay, I'll get the source code, I'll get the symbol table, and now I can read the original source code to find out how to hack the program. So we are basically assuming this is a black box. You do not have source code to the program, and even so, can we hack the program? And if so, how do we hack this program? Is that okay? So we'll go ahead and run the program, which is asking me for a password. I didn't bother to make a prompt to ask for a password. So I give it a password that is not the actual password, and it says right here, read define DMCA. Well, you can substitute define with other words that starts with an F. okay? But I'm going to use fine because this is a class. So RTF DMCA, okay? So there might be an actual password to make it work, but I don't know the password. But I really want to access the rest of this program. So what I'm going to do? So this is the exposure up to this point, which is is reading a password from standard input. Okay. So the first thing I might want to do is to say, okay, the programmer who wrote this might have made an assumption and say nobody's going to put in a password more than 255 characters, okay, or a really, really long string. Okay, so I'm going to run the program again, and I'm just going to randomly pick something that's kind of long. Nope, it didn't crash the program. And then we do it a little bit longer, and it didn't crash the program either. So the question now is, how do I know the program is going to crash, and what length is it going to crash? Doing it this way is not very productive because I'm just randomly testing stuff. So it would be nice, and in this case it is possible, to use a file. I'm going to remove all the password file that I have created up to this point because I want to do everything from scratch. So I'm going to do a password.txt file, and we're going to use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, okay? And we can do this like several times. So I'm going to do a $y, and then we'll paste this. Okay, there are 16 characters here, and I'll paste this 16 times, 16p. So now we have 16 times 16, which is 256 characters. Okay, it makes sense because each line has about 80 characters. So we're looking at 3 times 80, which is 240, and then plus 16. 240 plus 16 is exactly 256. So now we have 256 characters. Let's see whether this is going to crash the program or not. So we'll run the program again, and this time we are redirecting from the file, which means I'm not bothering to type all that stuff. I'm just kind of run this, and it is not crashing either. Okay, that's okay because we can just do this one more time. Okay, copy all the way to the end, and then do another paste. So now we have 512 characters. So we can see this approach can double the number of characters with each iteration, which makes it it wouldn't take too long to find out whether the program will crash or whether it would just kind of say, okay, your password is too long, it is not acceptable. So save this again, and then, oh, I erased the F, okay, put it back in. Okay, so we'll do it one more time. Aha! This time it has a segmentation fault. The program crashed. Okay? When the program crashes, by itself, it doesn't tell you much, but it does tell you that something is unexpected. Okay, the program, whoever wrote the program did not account for every possible case. And that's why it crashed. Okay? But that is an indication that there might be a vulnerability that you can exploit at this point. Yes, go ahead.
Would you get segmentation fault if you're trying to hack a program? Like, would it actually tell you the error, or would it just go blank?
It will give you a segmentation fault. So a program that is crashing will always give you a segmentation fault,
And
which is the first. Huh?
It'll tell you on the screen.
It might tell you on the screen, but it will crash for sure. The operating system will know about it. Because every time you have a segmentation fault, it is the program that is telling the operating system to go like, okay, I need to access this location, and then operating system checks the program space that belongs to the program, and go like, no, this does not belong to you. You may not use that. So the operating system always knows that there's a segmentation fault. And it can be Linux, it can be Windows, because all current versions of Windows are running in protected mode, which means when a program tries to access a certain memory location and it is not accessible, it generates what we call a fault to the operating system. And then the operating system can then decide whether the program should have access to that location or not. So it's always notifying the operating system. Okay, but this is not telling me a whole lot. So the next stage is to use GDB. Okay, so I'm using GDB not as a debugging tool, but more as a hacking tool at this point. There's a debugger in Windows and in DOS that operates pretty much the same way. Okay, so this is not a tool unique to Linux. There are equivalent tools in other operating systems. Yes?
Is it like the shell command for Windows? Or?
In Windows, I think it's just called debug, D-E-B-U-G. Whether the executable is still distributed with all versions of Windows, I'm not sure. But if not, you can probably download an open source debugger for Windows that serves exactly the same purpose. Okay, so I'm gonna GDB, the program, hack132.stripped, and this time I'm gonna use run inside the debugger, and then specify the redirection from password.txt, and it's gonna crash again. Okay, no big deal. We know that it's gonna crash, but this time it gives us a little bit more information, doesn't it? It tells me that it is attempting to continue execution at this location, 37363534. Just the way I spelled out the hexadecimal numbers, there seems to be a pattern to it. What do you think is the pattern? What is this? What is special about this quote-unquote address? It doesn't seem like an address to you. 2 hexadecimal digits makes up 1 byte, right? So we are looking at 37 as a byte, 36 as a byte, 35 as a byte, 34 as a byte. It is very unusual, okay, because every single one starts with 3, right? Mm-hmm. And then the least significant digit of each byte is also decrementing. That is highly unusual to be just random. Okay, so that's the first thing you might want to notice is, hey, this doesn't look like a real address. Okay, if it's not a real address, what is it? 34 sounds like an ASCII code. Anything from about 20 in hexadecimal to 7F can be ASCII code. So in this case, 34 is actually the ASCII code of the digit 4. 35 is the ASCII code of the digit 5, 6, and 7. In other words, maybe it's just coincidental, but maybe it is it's correlating to the password, which is filled up with what, 0 to 9 and then A, B, C, D, E, F. Is that making any sense? Sort of? Okay. So what we need to do now is to look at this and go like, I have a suspicion. Okay, this may be because of the password that we have. So one other thing that we can also take a look at, okay, this is you don't have to remember this because it is a different architecture. This is a stack pointer in this particular environment. It is equivalent to our register D. In other words, I can kind of examine what is on the stack right now. Okay, what the stack pointer is pointing to. So to do that, once again, this is not something that you have to remember how to do. I can examine 20 things. Each one is a byte, and I want to display each one as a character. And these things are going to be where the stack pointer is pointing to. Ooh, what are we getting back? 8, 9, A, B, C, D, E, F, 0, 1, 2, blah, 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 blah. That's the password. Okay, so apparently the password is so long that it overfilled the local variable area into the return address, and it was used, a part of the password was used as if it is the return address, and that's why we attempted to continue execution at location 534, 35, 36, and 37. Okay, so maybe it's a good time to take a look at the stack. Basically we want to look at what is happening on the stack at this point. So what is happening on the stack is kind of like this. So imagine this is your memory space, and this is a local variable. Okay, so this is what we call, I'm going to call this a string buffer. Okay, which is used to store the password, and we're trying to do some hash value of the password to see whether it matches something or not. Okay, doesn't matter what it is. So whatever password we enter in standard in is being copied into the string buffer. The string buffer is a local variable, which means it has to end some point. And this is a local variable. Okay, so we might have other local variables, but these are all local variables. At some point, the local variables will end, and then we have the return address. Is that okay? This is something that we already know. This is what we do with our toy processor architecture when we translate C code into assembly code. As it turns out, even though the instruction set is different on the i386 architecture, the way they utilize the stack is almost exactly the same as what we do in this class. Okay? So on top of the return address, we have the parameters. So we got param1, and then we got param2, and so on, okay? Which are not really of any concern to us as far as crashing the program is concerned. When you have a function that is kind of like string copy, strcpy, or something that relies on the terminator to stop the copying, then it is not what we call length delimited. In other words, it is ignoring, the code is ignoring the actual number of bytes allocated on the stack for that local variable string buffer. It will keep copying until it sees a null character, until it sees a Linefeed character, or something along that line. Which makes it possible, okay, so when I filled up the whole thing with 0, 1, 2, 3, 4, 5, 6, 0 to 9, and then A, B, C, D, F, it basically starts filling this thing up. It uses up the entire buffer. But since my password passed in is longer, the terminator is not seen at this point. The terminator is not seen until maybe up to here. So that means the password itself is not only overwriting what it should be overwriting, which is this portion, but it's also overwriting this portion too. It's also overwriting memory locations that it's not supposed to. And the most important part it overwrote is the return address. So when the return address is overwritten, and the subroutine says, okay, it's time for me to return to the caller, it's going to use whatever 4 bytes, in this case because it's a 32-bit architecture, it's going to use whatever 4 bytes is at that location and say, I'm going to return to that location. And that's why it returned to the location 34, 35, 36, 37 in hexadecimal. Is that okay? But we have a lot of 34, 35, 36, 37 in the password that we have. So it's time to go in and change that so that we can uniquely identify which one are we talking about, so that we can get one step closer to hacking this program. Are there any questions at this point? So even though it's a different architecture, the way the program crash is the same way as what your program would do if you are to copy things into a local buffer of a local variable beyond the allocation of the bytes.
Professor?
Yep.
What happens if you put is the backslash 0 the null character?
Uh-huh.
What happens if you put it into as a password and then?
That would not do a single thing because in this case it's copying from standard in. In other words, it's kind of the same thing as a cin and then greater than into a string variable. It is not looking for a null character. It is looking for a Linefeed character. So a null character would not stop it. It's going to stop when it sees a Linefeed character because it's a read line. It's reading the entire line, including and up to the Linefeed character into the string. So a null character would not stop it.
What is the Linefeed?
Huh?
What is the Linefeed character?
A Linefeed is ASCII 10. It's just one of the control characters. Okay, so getting back in the good old days, with typewriters. Okay, well, I mean, all of the control characters that we have were one time intended for typewriters or teletype terminals. So a Linefeed is basically the drum of a typewriter, rotating this way. So you're literally moving on to the quote-unquote next line. But it doesn't move the head. It doesn't move the carriage itself. Okay, and that's why the return character, which is ASCII 13, is called carriage return. Because when you type, okay, so when you type, the carriage will move this way. Okay, assuming you're using a language that goes from left to right, because not all languages go from left to right. So assuming your language is going from left to right, your carriage is going to move this way, right? So when you're at the end of the carriage, or when you're at the end of a line, you have to do two things. One is a carriage return, which moves the entire carriage back to all the way to the left-hand side. And the other one is called Linefeed, which rotates the drum so that you're ready for the next line. Okay, so depending on which operating system you're using, in Linux, it looks for a single line feed character to mark the end of a line. In DOS, it looks for carriage return and line feed, 2 characters to mark the end of a line. On Mac OS X, it looks for a single carriage return character to mark the end of a line. So that's why when you edit text file, like plain text file, and you send it to somebody, if you edit it in Notepad in Windows and you send it to somebody who's using Mac OS X, it will show kind of funny on the Mac computer. But the other way around is even funnier. Okay, if you edit it in, yep, exactly. So in Linux, because we only use a single line feed character, and you send that text file to someone who's using DOS and you try to open it in Notepad, everything is on one single line. Because DOS says, I do not see any combination of carriage return and line feed, so it's one single line. So this is, even to date, it is still kind of an issue, but most editors are smart enough to go like, okay, I see a single line feed, this is probably coming from Linux. So for the rest of the file, we'll just assume that a single line feed marks the end of a file, marks the end of a line. So most editors are smart enough now. Okay, so did I answer your question? Okay.
Would the same thing work if you now put in the line feed character? Or there's no representation for line feed?
The line feed character, when you use, when you say man ASCII, the line feed character is 10, or in decimal it is 10. This is the line feed character, LF, line feed. And then carriage return is 13 in decimal, or 0D in hexadecimal is CR for carriage return. So those characters usually are difficult to type in, because when you're in an editor, the moment you press the enter key, it is going to put in whatever it takes to end the line instead of just putting in the character. But we got some tools to do that, to basically edit the file any way you want to. So we'll get to that part. Okay. All right. So getting back to the password file, we got we know it's one of these 4, 5, 6, 7s that is being used as a return address, but we don't know which one, right? So we're going to have to do some replacement here. So we'll replace this one with A. We're looking for 4, 5, 6, 7. Okay, we'll replace the next one with B, C, D, E, F, G, H, I. And you can see this part is kind of tedious. You can easily write a program to do it. Okay. I'm just doing it by hand, just to show you guys that, yep, I don't really need any special tools to do this. J, I, J, K, L, M, N, O, P, Q, R, S, T, T, next. U, V, W, X, Y, Z, and then uppercase A, B, C, D, E, F. There we go. So now we can distinctly, figure out which one of the original 4, 5, 6, 7 is overwriting the return address. Is that okay so far? So we save this file, and then we have to use GDB to see it, because otherwise it's just a crash. We cannot see the pattern of the quote-unquote address. So we GDB again, and then we specify the executable, run it again, and redirect it from password.txt, and it crashed again. Okay, not surprisingly, but this time we know that the character, the first one, is not a 4 because we replaced all the 4s with a letter, right? So we now know that the ASCII code is 72 in hexadecimal. Now I cannot remember the ASCII code of this stuff, so we'll just have to use an ASCII table to figure it out. So we say man ASCII, and then we just look up, and go 74 in hexadecimal is the ASCII code of R, lowercase r. So now we have singled out, the 4 bytes that are being used as a return address. Okay, so we go into the password file, and then we look for R567, which is so these 4 bytes over here. These 4 bytes basically is being used as the return address. Whatever bit pattern we put here will be used for returning. In other words, I have control over where the program can go to continue execution. Okay, so that solves the first part of the problem, which is, how do I gain control? I gain control now. But now that I have the steering wheel, where do I want to turn it? Okay, should I take a left turn? Should I go straight to it? Should I make a right turn? Well, that's the next stage. Are there any questions about how I hijack or commandeer the steering wheel? Yep.
I have a question about how you keep track of the amount of characters you put in, because they're not really highlighted by sections of 256 characters. You put in 512.
Yep.
And that looks like halfway. But
Yeah, that looks kind of halfway. It's a little bit more than halfway because I'm suspecting the buffer is only 256 characters long, but there are some additional. Okay, let me pop the so-called document camera. So I'm suspecting that. Okay, I'm not sure. Can you guys see the hover? The little kind of faint gray dot. Sort of.
yeah,
Okay.
oh,
A little bit? Okay, maybe I cannot use it. I cannot rely on that. There. Okay, I'm going to use green here. Okay, so the buffer itself is only this big. This is the entire buffer. But overflowing the buffer itself does not immediately give you access to the return address because we got some additional stuff here. That's the additional part of the local variable. So you have to overwrite that portion too until you get to the return address, which is here. So that's why it's not immediately after 256 characters that we got control. It is a little bit beyond that because there's some stuff between the array that we are overwriting and the return address. There's some additional stuff there. Is that okay?
yeah.
All right, cool. And yes, this does look like a pencil. They make an active stylus in the shape of a regular Stedler pencil. And it's also made out of wood too. Yep. So people who like to chew on their pencil can now chew on a tablet stylus the same way, and they give you the same taste. They use the same paint too.
People who lose pencils can also lose their stylus easily.
Oh yeah, it's going to be a little bit more expensive now. Okay, so we know these 4 bytes are what we need. The rest we don't really need anymore. Okay, because the rest is really stuff that is beyond the return address, which is of no use to me anymore. Are we doing okay so far with this? Okay, so we got the steering wheel, we got control at this point. Now I need to know how do I want to steer the bus? Okay, because right now I got the steering wheel, I'm just jerking it and I'm crashing. Yep.
You can see where the stack pointer is pointing to. Why don't you just look at it when it's pointing to the return address and know what the return address is?
It's going to show you where it is supposed to return to, but not where I want it to return to. Okay, so that's a very good question. Now let's go ahead and start a new slide here. Okay, so I'm suspecting, as a hacker, I'm suspecting that the program has something like this, which is not unreasonable. Okay, so I'm going to use a fine, because I use a fairly low resolution canvas, so that's why the thick pencil looks a little bit too thick to me. So it is not unreasonable that the hacker will suspect that there's code that looks like this. If calling some yada 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 routine, this is the code where authentication is successful, authenticated, and there's a bunch of code here, else, print, RTF, DMCA, exclamation point, blah, 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 like that. And there might be some other stuff too. But that's not unreasonable to suspect that there's a conditional statement of some kind where if it is not authenticated correctly, it goes to the one branch. If it does authenticate correctly, it goes to the other branch, right? So what I want to do is to say, once I hijack control of where I can go to continue execution, I am going to force the program to go here. This is where I want to go. In other words, whatever subroutine is crashing doesn't really matter. It does not matter to me. I just want the program to continue execution here. Is that okay? Now, it does not work sometimes, but sometimes it works. Okay, so it all depends on what local variables are being used, and a few other things. So, but in this case, we'll at least give it a try. Is that okay? All right. So, given this is the assumed program, and I have control over where I can go to continue execution. I can go anywhere now because I can control the return address. How do I find out about this part?
Can you use GDB to see where the program is when it's prompting you for the password?
You can, but the place where you're prompted may not be even close to the place where the stack overflow is occurring. Okay, and my concern is really the destination. I just need to know where am I supposed to go in order to go straight into the authenticated branch of the conditional statement. So what is the one clue that I got at this point? If you look at the screen, you look at the behavior of the program, what is the one clue that I got at this point?
The print is?
The string, right? The string, RTF DMCA. Okay, and it just so happens that all C programs, okay, will store a string as an initialized array that is internal to the program. So it has no name, okay? There's no name associated with this particular array of characters, but it is stored somewhere in memory. So my job now is to search for that and go like, let's find out where it's going to print RTF DMCA, RTF DMCA exclamation point. Does that make any sense? Okay. So the first thing I can do is to confirm that it really is there in the executable before I go even further. Okay. And there's a program called Hex Dump. Okay. If there's none, you can easily write one. Okay. Hex Dump is all it does is it will go through every single byte of any file that you feed it, and it will just dump out each and every single byte. In this case, with dash uppercase C, it will print everything as a character if it is printable. Okay, it's just a little nifty, handy tool, and you do it to the entire program. And I'm going to pipe it to less, which is equivalent to more in Windows. So we have this something like this, and we're looking for RTF, okay, which is unusual to be just naturally occurring by itself. So right here we found it. We found RTF. And it is a string, we got the whole string, RTF DMCA. And right before that we see welcome back trusted user. Whoa. That gives me some clue, don't you think? Yeah? Okay. I like this.
Does this give addresses? Does this
No,
give
not
addresses?
yet. Well, it will give you the offset into the file where this is found, but it doesn't give you the address of when your program is running, what is the actual address. It doesn't give you that. Okay? So right now I have confirmation that this information is indeed somewhere in the executable. Okay? In some cases, some people may store a string in a encrypted way, so you're not going to see the actual literal string. So in those cases, it will be much harder to crack because you cannot see what message you see on screen to go back and say, okay, where is that printed in the code? Okay, but in this case, it's all in plain text. I can actually do it. Cool. All right. So now we can go ahead and use another tool. The other tool is called Object Dump. Object Dump is going to dump executables or object files, and when you do a man page on Object Dump, obj dump, it says it'll display information. And one thing it can do is it can disassemble, okay? And it can disassemble all, I'm gonna try dash lowercase d this time. I tried the other one in the other class. It can also display all headers, which is dash x. We want to show all the sections. So let me see if I can find the part. Section headers, dash h, okay? So we can look at dash h and dash lowercase d, okay? Obj dump, dash lowercase d, dash h, and then we have the program name, pipe to less, okay. So what you're seeing right here, this is the actual code, assembly code for this particular architecture. Now, because we're dealing with i386, the instruction set of i386, it has different instructions, but you still see something that we recognize, like subtraction, addition, except the order is different. So in the case of add, it is adding the first item to the second item, and it's stored in the second item, as opposed to our order of the specification. But for the most part, okay, you can see that, hey, we can understand some of this stuff. It actually has a call instruction. So instead of using the 5 lines that we have to do, LDI, A with a return label, decrement D, STDA, and then do unconditional branch, and then the actual return label, instead of using 5 lines, is a single instruction, single opcode. Yep.
And push seems to be like 3 lines, right?
Huh?
For us, push is like 3 lines.
Exactly. For us, push is, no, this one is only 2 lines, because this one is pushing just a register, which only involves decrementing D and then the ST instruction. And then the pop here, which is to retrieve whatever the stack point is pointing to into a register, is also 2 lines for us. But the ASCII processor has specific instructions to do that. The return that we do has 3 lines, right? So we have an LD instruction followed by an increment D followed by a JMP instruction. Is a single RET instruction here. So this is definitely a CISC architecture because it offers you a lot of quote-unquote complex instructions that can just combine a few things that we do with our processor in different instructions. But as a result of this, this processor needs more silicon. Okay, so the die is bigger because it needs more silicon, and then the second side effect is it may consume more power as a result of that. Okay, but what we're looking for is the string. Okay, so we look through this whole thing. We go like, okay, let's see if it doesn't have any string sections. Okay, it doesn't display any string sections. So what we'll do next is kind of I have an idea of what we're looking for, but it doesn't show it here. Okay, so that's why we'll disassemble all. Okay, we'll just do a dash D, okay, uppercase D. So now it's going to disassemble all sections instead of just the sections that are supposed to contain instructions. Okay, same thing, but this time it will have, it will have more sections available. But you're not going to find RTF DMCA because it will attempt to disassemble those bytes as if they were opcodes. Okay, it sounds like it's not going to help us much. But what we can do is to find out, okay, how do we spell RTF in ASCII code? So I'm going to use another terminal here just to look at the ASCII code. And then we look up RTF. Okay, so we have R, which is 5.2 in hexadecimal. Okay, so I'm just writing it down on the side here. So we're looking for 5.2, and then T is 5.4, and then F is 4.6. Okay, so those 3 should be good enough because the natural chances of these things happening, these bytes occurring right next to each other, is pretty slim. Okay, so now we go back to the other one and say, okay, locate everything that has 5.2 because that's the uppercase R. Okay, and let's see what What did it find? 5.2. Pattern not found. Pattern not found. 5.2. There we go. Okay. That's the part of an address, which is not what we want. We got a 5.2, but it's not followed by 5.4. We can ignore that one. Once again, this is an address, and it's definitely not followed by 5.4. Ignore that one. Ignore this whole bunch because they are addresses. Aha! 5.4, 5.2, 5.4, 4.6. And then DMCA is 4.4, 4D, 4.3, 4.1, and the exclamation point is 2.1, and then 0.0 for no terminated string. We found it. We got it. Okay? But the nice thing about object dump is whatever you see here is the actual address that the program will see when it's being run. So in this case, we are looking at the address of 804856C. The B refers to the 00, so the byte that we're interested in is going to be 6C. Is that okay? So we'll write it down. So now I write down that in my notepad. So I'm going to write down 8048 56C. Okay. And you can see on the screen too, I just wrote down that particular address. So now we go look for that address, okay? Because maybe we're lucky and find that, and some other times we may not find it, and we are super lucky. Yep.
So this one could be also, so if you were to replace the last 4 characters with the 856C, it would take you straight to that address. So you know how like if we change.
Yeah, but that address is corresponding to a string which you cannot execute.
Oh, okay.
So we are a few steps from what we really want to accomplish, because right now what we have accomplished is we have located this line here. We have found where this is, which is presumably close to where we want to go. Is that okay? All right.
But I'm saying, so if we do have that line and you were to replace it, like the last 4 addresses, as soon as you run the code, it just, even though it's overfilling or messing up, it's still technically taking you to the print.
Yep, exactly. But we don't want to go to the string itself. We want to go to the other branch of printing that particular string. Yep.
Don't we know where what the other string says? So can we find that and go to that string?
We can do that too. Yep. But we want to go to the beginning of the branch. So either way, we have to analyze the code a little bit. Okay. Cool. This is really cool. So now we have found, where the branch is, or the location of the branch that gives us the unauthenticated message. Okay. So looking at this code, even though we haven't really talked about the I3, D6 instructions, certain things are kind of mysterious, but other things, should still be kind of obvious. This is an unconditional branch instruction. Jump. Okay, it's not jump I. It doesn't have JMP-I because the syntax is different. Okay, but it is nonetheless unconditional. Now, if that is an unconditional branch, okay, how will I get here? Which is right before, this is the code to set up the printing of RTF DMCA. So how can we get here?
The conditional jump above it for the if statement should send you directly to that line.
Yes. So what we have seen at this point, okay, if I were to switch back to the documents camera, we have located the JMP at the end of this branch because this jump has to jump all the way to the end of the conditional statement. We found that unconditional branch, which also means this jump here marks the end of the then branch. And the then branch most likely is corresponding to what happens when authentication was successful. Is that making any sense? Because we found the else branch, and now we say, oh, we found a unconditional branch like a few instructions before what we have located. That has got to be the branch around instruction for the then branch. Now it can be opposite, can be reversed, but in either case we can analyze the branching in order to figure out, okay, which branch are we in? How do we get to the other branch? Is that okay? All right, so now that we have located the other branch, okay, this is the end of the other branch. Where's the beginning of the other branch? All right, so this is how you analyze the code. We know that there's a conditional branch to get here, to get to the else branch, right? And the location of this branch is yada, 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 AB. Okay, we just have to remember the least significant 2 digits. So there has got to be some kind of branch, conditional or unconditional, to go to 80484AB. Can you see that? There's a JE instruction, right? Now JE is the same thing as our JZI, compare if equal to, okay? So this is the conditional branch to go to the else branch, which also tells us that this is the beginning of the then branch. So between this sub instruction, which is from this location, all the way to the unconditional branch, this is our entire then branch corresponding to what happens when authentication was successful. Is that okay? Is that making any sense? In other words, we are disassembling the program, but only locally, to where it matters to us. Yep.
Does the test matter in this case?
Huh?
Like instead of actually
Nope.
going through?
Nope. The test does not matter to me. I need to bypass the conditional branch altogether, because the conditional branch is what made the program decide, you entered the wrong password. Okay. I'm not going to give you access to the program. So we want to bypass the entire thing and go straight to the code that corresponds to, yep, you got it, here it is. Okay? Go straight to that point, exactly. Okay. So we look at this address, okay, go like, okay, this is where we want to go. We write it down. Okay, so we write that address down. So we write down 8048499. Okay. And then we switch back here. This is the address that we want. Okay, it consists of 4 bytes. Here's 1, 2, 3, 4. So we got 4 bytes here. But when you have 4 bytes and you need to express these 4 bytes sequentially, then the question is, which byte do you specify first? Remember, this is all going to go into the characters of the password, right? So which one is the first character, which one is the second one, and so on. That part depends on the endianness, E-N-D-I-A-N, endianness of the processor. The Intel architecture is what we call a little endian processor, which means it stores the least significant byte first. So in this case, 99 is the least significant byte. So in the password file, we'll have to specify 99, 84, 04, and 08. If you have a big endian processor, then it will be the other way around. You specify 08, 04, 84, and 99. So you have to understand the architecture in order to apply this hack. Is that okay? What about the toy processor that we have? Does it have any inherent endianness? The answer is no, because it's an 8-bit processor. It can only deal with 1 byte at a time, so it has no endianness. Endianness only matters when you have a processor where the registers are multi-byte. Okay, it can be 16, 32, 64. Okay, the question is, when you store a 16-bit register into memory, which is byte addressable, which byte stores the least significant byte, which byte stores the most significant byte. But if the processor is an 8-bit processor, it has no innate ability to deal with anything more than a byte, so it has no endianness associated with it. Is that okay? Other times, you also have to deal with endianness in communication protocols, like TCP/IP. TCP/IP is, interestingly, big endian. In other words, when you want to transmit a 32-bit number, like a packet length or whatever length they want to specify, you have to transmit the most significant byte first. which is not what the Intel processor natively wants to do. So you have to be careful, okay? Because when you write a C program, you go like, okay, we're gonna put this integer into this string here to be transmitted. Nope, can't do that. You have to remember to flip the order of the bytes first, because the processor natively is little endian, but the communication protocol is big endian. Okay, so we're almost there. So we just have to put this one into the password file. But that's a difficult thing to do, because 9984 are beyond ASCII. Okay, what do I mean by that? So when you look at the ASCII table, and you go all the way to the end, okay, you can see that 7F is the last ASCII code. It corresponds to the delete key on your keyboard. That's the last one. 80 is technically not an ASCII. Okay, which also explains why char is signed. In C and C++, when you say char ch, ch is signed. It can represent negative values. Okay, but it's not helping us here because we can't really type these 4 characters into the file. Okay. Well, that's why we have another program to help us to do this. You can see I have all the hacker tools installed on the Power Server. It's called HexEdit. Okay, so HexEdit is kind of like Hex Dump, except it allows you to change the bytes. You just have to enter the hexadecimal digits for the bytes. So this time I'm not interested in changing anything in the program or the executable itself. I'm changing the password. So I'm going to go to the last 4 bytes here. And then I just need to move this up a little bit so I can see the 4 bytes that I need to change these 4 bytes to. So there'll be 99, 84, 04, and 08. That's how you kind of inject actual byte values into a file. When this is all done, Control X will get me out. Oh, I need to save it first. Okay, forgot to save it. So 99840408, and then we need to specify Control X. There we go. I type Control C instead of Control X. So specify yes. Okay. So now the password file is indeed modified, and then we will run the program again, and we'll run it not in GDB this time. So we say hack132.script and redirect from the password file. And this time it says, welcome back, trusted user. Now it did have a segmentation fault at the end because I did mess up the stack. Okay, so it was not able to recover everything to make the program run normally. But I did at least get to the branch that I'm not supposed to be able to get to. So that's hacking the program. But it's okay this time because I'm giving myself permission to do it. Why is this useful? Yeah, go ahead.
Would it be possible to fix the stack and let it continue running? Or?
That would be kind of difficult. You can. The reason why it's difficult is because we are relying on the stack to overflow to get to the place where it's supposed to go to. So it is a little bit difficult to kind of track down how it uses the stack prior to getting all that stuff overwriting this on the stack, but it's probably possible. That's a good question. Let me see if I can do this. But before we do that, we'll do some analysis first. Okay. So we'll switch back to this. Okay, this is a new page. All right. So that subroutine is probably called by somebody else. So this is what we call a frame. It corresponds to basically the stack used by an invocation that is the caller of the one that we want to crash. Is that okay? And this is the one. Okay, this is the frame to be hacked, and this is the frame of the caller. Of the caller to the frame that is constructed by the subroutine that is being hacked. Okay, so when we filled up the password, and overflow the stack, it is overflowing this one. Is that okay? Which also means, at this time, okay, it's going to consume the 4 bytes used for the return address. So the stack pointer is actually pointing here, which also means, if I look into here, I can possibly, find out, who the caller is, and then I can potentially figure out where to put a breakpoint, because if I know the address, I can put a breakpoint in GDB without source code. So then I can single step through the whole thing, and then figure out, okay, how did we get here, and what the stack really should look like at that point, so that we can customize the password file so that we are only changing the 4 bytes that we're supposed to change, but leaving everything else the same. So that is possible, but it takes a little bit more analysis. But it is doable because the rest of the stack is still intact. So that gives us a chance to look at, okay, who called the subroutine that is being hacked, and what are the addresses corresponding to those things, and then we know where to put breakpoints. Yep, go ahead.
I was thinking if there is sort of like a test to see if it compares what you put into password, right?
Mm-hmm.
So can't we find where it tests it and find what is
You can, but in this particular program, okay, I lost the source code already, but I intentionally make a mistake in the source code so that there's actually no way to get to the authenticator branch. Even when the program is running correctly and you type in the correct password, I put in a logical flaw that even if you put in the correct password, it still would not let you go to the authenticator branch. So I bypassed all that logic completely to get to the authenticator branch, even though it was impossible to begin with. So that's some hacking. All right, so why is this useful, okay? So the reason why I mentioned this in this class is because now we actually understand enough about what is happening on the stack when you're calling a subroutine. And that's why I mentioned this. The second one is I just want to expose computer security, cyber security, hacking, and those concepts to all of you, because I think it's a good thing to do. Good in many cases, in many different perspectives. One is career, okay? So what do you want to do after you get your 4-year degree in computer science or computer engineering? I'm assuming most of you are computer science or computer engineering with a few in electrical. So what are you going to do? What is your inspiration? You want to become a game programmer? A database programmer? What is your plan? Nobody has thought about it?
Virtual reality.
Virtual reality, okay. That's going to be big. What else?
I was thinking that you're also going to show us the limitations of using certain data types when you're using the stack, like how it can be overloaded.
Well, it is how you deal with strings and arrays in this case. And it's particularly, these problems only happen when you're doing in C and C++. It won't happen when you're doing in Visual Basic or any scripting languages. Because in C and C++, it has pointers, and you can dereference pointers anytime you want to. And that is the Achilles heel to C and C++ programming, is you can do stuff like this. Okay? Okay, but getting back to your career choice. Okay, so have you guys thought about what you want to do after you get your degree? Or are you guys just gonna like, I'll just go with the flow, whatever job is available at the time?
I was thinking,
Okay, yeah, go ahead.
Research in graphical modeling.
Graphical monitor?
Modeling. Like
Modeling,
applications.
okay. So that's pretty cool. Has anyone thought about getting into cybersecurity?
Someone.
Okay, so a few, okay. Cybersecurity is definitely one of the least glamorous, field in the industry. If you get into robotics, you get robots to show, right? You get the bipedal, the quadruped, type of robots. They can leap, they can jump, they can attack people, right? Cool. All right. If you get into 3D modeling, you get to show all the cool stuff that you can do in 3D modeling. You can do game design, okay? And you can show people, oh, look at all these cool games and whatnot. You get into computer security, they go like, so what do you do? Well, I stop people from hacking into the system. Oh, okay. And that's it. It's not glamorous, okay? But when you think about your career, okay, glamour can be one part of it, but what are the other criteria for selecting or choosing your career path? Salary and?
How long it lasts.
Job security, very good. Okay, so those two are kind of important too. So when you look into game development, okay, what is the job security and what is the pay? What do you think? I asked the same question yesterday, and one of my students said, almost every single big game development company, they fire like 75% of the developers when the game is done. They keep the best 25% and fire the other 75% because they don't need them anymore. They don't need people to do all the chore, the actual grunt work anymore. So they fire all of the 75%. And how well do they pay? Well, it depends on how your competitors are paying, right? Because nobody's going to pay much more than what the current rate is, right? What about the length of the career in game industry? Well, sorry.
Or you mean the whole industry?
Yeah, whole industry.
Oh, it's getting shorter.
It's a big industry. Okay, it's a huge industry. When you look at the actual revenue of the computer gaming industry, it had exceeded Hollywood years ago. I think for this year, I would not be surprised if it is 3 times the revenue of Hollywood. Easily. Okay, so there's a lot of money, but does that translate to job security?
There's an influx of people there.
Exactly. It doesn't really need a lot of special skills. And for the most part, game design require creativity, with storyboarding, character design, that sort of stuff. The actual hardcore part of programming, which is the game engine and also the physics engine and stuff like that, does not move very quickly because it doesn't have to move very quickly. There's no push to do it. Okay, if your game engine running on existing hardware is realistic enough, the frame rate is good enough, the physics engine can emulate physics well enough, why change it? There's no reason to change it. Okay, so how the game companies compete with each other now relies on gameplay. It depends on the storyline. It depends on how many modes do you have. Can you do PvP versus co-op versus blah blah blah. Okay, but those do not involve a lot of programming. It really is just someone who's directing how to play the game. Does that make any sense? So that means job security is not really all that good. What about security? What about cyber security? What guarantees, or not guarantee, but what makes cyber security have more job security?
There will always be black
Which
hats.
is kind of, huh?
There will always be black hats.
There will always be black hats. Why? I mean, in the game industry, there's always competition too.
Because it deals with actual money, banks, and
Yep.
there's more risk.
There's a lot more at stake, right? So imagine, some countries. Okay, we are not talking about individual companies where gaming is. Okay, you have EA, pit against another giant of gaming company. But in computer security, you're pitting countries against each other. Who is trying to hack into the Air Force database of the United States? Everybody. Okay? Now, different organizations, different countries may have different capabilities, but they all want it. Okay? Who wants to hack into President Trump's cell phone? Everybody, but they don't need to.
It's all Twitter.
But yep, because it's all tweeted out. It's like there's no secret on the phone. Forget it. No need to hack. Okay. So now you think about all of this. Then you think about the change of the stuff. Okay. Remember what I said about game engines? They don't really change very rapidly because as long as it is okay, the frame rate is good, it looks realistic enough, there's no need to change. What about in cybersecurity? Does it change? It changes all the time, right?
There's a recent report with what's it called? The Wi-Fi encryption method, WAP.
WPA2.
Yeah,
Uh-huh.
used for a while now. It's also does some good walk around.
Yep. And also, rainbow tables, okay, makes MD5 hash totally useless, basically, right? So that field changes all the time. People find vulnerabilities in really core parts of an operating system, and then you have to fix it. You have to first detect a problem. And then once you detect a problem, you have to find out how much damage is being made or has been made, and then you have to fix the problem, okay? So because it's an adversarial kind of situation, it's not competition, it is adversarial. And you're dealing with, the rest of the world, okay? And I would not even be surprised if someone is to say, but you know what, the FBI actually is always trying to hack into the database of the CIA. I would not be surprised, frankly. Or the other way around. NSA is trying to hack into the CIA database. Okay, I can see that happening. Okay? So that means job security. What about pay rate? How well will they pay a game developer? And why do you think that's how much they pay for game developers? Okay, switch around, okay? Turn your chairs around, not literally. But imagine that you are the employer, okay? You own this game company, or you're the supervisor or manager, and you're trying to hire game programmers. What will help you set the pay rate for your developers? What would you use? Yep.
How many there are?
Okay. How many good programmers are there available, right?
Yeah.
Mm-hmm. And what other game companies are paying, right? So you basically just have to match what the other game companies are paying. So what do you think, how much do you think the game companies are paying for their game developers?
As low as possible.
As low as possible, very good, okay? As long as they can keep some of the good programmers around, it's good enough, okay? So if you're one of the top-notch people, yes, they might pay you a lot of money to retain you. But for the most part, if you're one of the grunts, okay, doing the chore of programming, they're not going to pay you a whole lot because every single university is cranking out a lot of people graduating with a computer science degree, and they can all do the grunt work. But when you get into computer security, there are all different ways of getting into computer security. So the chances of you finding a niche and go like, I'm a specialist in this type of computer security field is a little bit higher. And then they also, if you know something that is important, they also want to make sure that you don't get hired by somebody else. The CIA will say, I don't want you to be recruited by the NSA. But wait, this is all part of the United States government. Yes, but it's a different agency. I don't want you to go to a different agency. So they will have to use different ways to keep you working for that particular branch of government. Getting paid is one. Okay, this is our pay scale. We are better than the other one. So there are a lot of factors to consider, to kind of at least think about computer security or cyber security as a possible career in your future. Yep.
If you turn AI towards the security scene, wouldn't that make it too complicated for humans?
It depends on how you can apply AI in this case, because computer security is not pattern recognition. Now with pattern recognition, yes, the computer can actually do a pretty good job, finding things that match a particular pattern using neural networks. You can present a picture of someone and say, okay, search for this person in Google, and they will find people who look like that person in various ways, which is kind of creepy. But computer security is not like that. Okay, computer security needs very specific skills, and you need to really use analysis skills to get into something, to figure out what happened, and so on and so forth. So it's not something that the neural net type of AI can really apply to, at least not now. Now, some of the other branches of AI, like automated theorem proving and stuff like that, may be applicable, but definitely not neural nets, not at this point. So that means, you know, it has a little bit more shelf life at this point, you know, because even though we can automate and use AI for many of the other things that we do, computer security or cybersecurity is still not one of those things where AI can replace people. So, you know, kind of look into it. You know, it's something that is kind of interesting. And by introducing these topics, this is just, you know, just a toy kind of thing. Okay, you know, this is not in any way, you know, oh, this is really how people, you know, hack into other programs. If you guys are interested, I would look up CCSF, or City College of San Francisco. There's a professor called Sam, I cannot remember his last name. The one last name that popped up in my mind is Sam Wise, which is not, Sam Bond? He's the guy, okay? So basically, look him up. I took a few classes from him in, you know, like a 1-week class, and he's really interesting. He talks about a lot of stuff, and he definitely is one of those people who think out of the box, and he finds vulnerabilities, you know, left and right, and they tell people about, you know, all the security flaws that he finds, and people go like, oh, okay, it's okay, no, not a problem. He found a way to use a Python program to wrap around a known virus, and then put it into a file system, and no virus checker was able to find it just because it was wrapped by a Python compression program. And go like, okay, you know, he went to different antivirus companies and told, you know, each one, and go like, hey, I can slip a payload through, you know, through the Python encryption, not encryption, not even encryption, it's just compression. And then none of the other companies actually were interested. Go like, oh, okay. But they really should be paying more attention. So anyway, if he offers, you know, online classes, or if he has any type of recording, you know, this is one of the really cool places to go if you want to get into computer security. So he has, you know, right now he has classes on DNS, or domain name server security. That's a big deal. If you can compromise a DNS server, what's going to happen?
You can tell where packets go to our computers.
You can redirect packets, right? So now you can say, wellsfargo.com is not here. Instead, it is over here. Okay, and then people can look into the URL. It's not spoofed. The URL clearly says you're at wellsfargo.com, but you're not at wellsfargo.com because they hacked the DNS server. So hacking a DNS server has a lot of consequences. Network security monitoring, you know, basically how do you spot problems, okay, you know, as early as possible. Ethical hacking, which is sort of what we just did, but he goes in he will talk about a variety of, you know, ethical hacking in his class, and it's also different from our own ethical hacking classes here on this campus. He goes, you know, deeper into the mechanisms and how to do things. Advanced version of that, IT security, cryptography, internship and work experience. Basically, you know, he's placing students in companies that basically have jobs related to computer security. And this is all in San Francisco, and you can probably imagine how many companies students as interns can participate and get their feet wet, so to speak. So this is really kind of cool. If you're looking into computer security, you can start with here, and he put most of his notes online too. So if you click on one of these, I would not be surprised if you find his entire syllabus online, along with the textbook, and also, you know, topics that he would go over, like lecture notes, projects. Okay, so you know, you can basically self-learn a lot of these things just by following, you know, these topics. So for those of you who are interested in this kind of stuff, don't do it now because you got an exam on Tuesday, right? Okay, so after this semester is over and when you have free time and you're interested in computer security, this is one of the best and free resources to learn about computer security in a wide spectrum too. It's not just, you know, one little thing, it's like a whole lot of stuff. Okay, any questions?
Will it teach us to change our to change our grades?
Hacking into the server to change your grade? Well, I think the DMCA may apply in that case.
Yeah. Then we won't need to study for these.
Actually, there was one professor, teaching. I cannot remember which university, and the homework assignment or the entire semester was about hacking into a server that stores the grade, and that's how people get a grade. It's like everybody starts with an F. If you can hack into the server and change your grade, that's your grade that you're going to get out of the class. Now, obviously, in that case, the system intentionally had security flaws, and the students basically have to learn all the techniques and be able to apply all the techniques to find out what the flaws were, and then figure out a way to get into the database and then change the record. But that was a class like that. There's also in industry, for those of you who are kind of looking into this, it's called DEF CON, I think. DEF CON, DEF CON. Okay. Nope.
One N.
Korean rep.
One N.
1N. 2017. There we go. It's an annual conference, and the interesting thing is everybody knows everybody there. The black hats, the gray hats, and the white hats, they all go and they all know each other, and then they all try to learn from each other. It's kind of strange, but that's a but that's one thing that you might want to consider if you're looking into computer security as your career choice. If you have time to go to one of these conferences, it will open up your world. Okay, it will. Yeah, go ahead.
They have all of their, a lot of their videos on YouTube you can watch. And there's some actually really hilarious ones as well. Like one guy who made a bot for World of Warcraft to gain lots of gold, and all of a sudden, within after a couple months or years of doing it, he got a sudden cease and desist from Blizzard with him and telling him that they were suing him for $1 million.
It's like, thank you for your advertisement. Okay, so to end today's lecture, I'm going to use NSA. Just type in NSA by itself, and you will see the news articles from really recent. Okay, this is one, and this is another one. There we go, just two. Okay, that's cool. This is from Monday, this Monday. Okay, so it's relatively fresh. NSA cyber weapons turned against them in hack. In other words, what the NSA has done is they have discovered zero-day exploits, which means those exploits have never been deployed or used before, and as a result, Microsoft doesn't know about it. The antivirus companies do not know about those, and only the NSA knew about those. Okay, so they're really good weapons to use because nobody has defense against it. So they stockpile some of these, what we call zero-day exploits, and then the NSA, computers got hacked, and other people stole their zero-day exploits from the NSA, and then used those zero-day exploits against the NSA. Yep, not pretty. And then this is another article. NSA struggling following major leaks. So you can read these articles, but what the point is, cybersecurity is real. I mean, there's no denying of the importance of cybersecurity. And now we are converting a lot of our weapons into self-driving, automated, type of automata. And you can probably imagine, the importance of cybersecurity is even more than before, because all the drones are fully autonomous. Okay, the warships are mostly run by computers. If you look into the okay, I can destroyer Elmo. These two words will find me what I'm looking for. See, told you. Because it's a Zumwalt class of its destroyer, and Zumwalt, which is the last name of the rear admiral, has a first name of Elmo. And not only is that kind of funny, but the captain of the first ship, there are only supposed to be 3 of these ships. The captain of the first one is James T. Kirk. I'm not kidding you. I kid you not. But the T is not the same.
Yeah, Tiberius.
Yeah, it's something else,
Yeah.
but it's James T. Kirk. So that's how you can tie in Elmo, James T. Kirk, with a super high-tech, destroyer, which they call this a data center on top of a huge electric generator. That's how they describe the destroyer. Why would they describe a destroyer as a data center, okay, on a huge generator? Because that's how the next generation of warship will look like. Because they don't use, they have conventional weapons, like a big gun and stuff like that, but it's also a platform to test rail guns, to test laser weapons and stuff like that. But it is also run almost 100% by computers. Okay, if they allow that, I think the technology does allow this ship to be run completely remotely. So the captain can be on the beach somewhere with a tablet and go like, yeah, I'm gonna go here. I'm gonna fire a missile that way and click, double click, and then click the button and go like, okay, now where's my drink? I would not be surprised if that is actually technically possible. So where would computer security come in? You can probably imagine what happens when the systems are compromised on a ship like this. So kind of think about that, because I know computer security is not glamorous, but in terms of career choice, it may be something that you might want to at least look into. And if it's not your cup of tea, fine, but don't dismiss it, just because it's not, on the front. It's not on the front line of news articles. All right. So I'm going to go to the lab in case any one of you want to talk about the topics that we have covered up to this point, or have any questions about the practice exam, or any questions related to what we'll be testing next Tuesday. So exam 2 is next Tuesday. Open book, open notes, anything that is handwritten or printed prior to the test, you can bring, just like with the first test. Okay, so I'm going to end the lecture here.